Hey guys, this is AP Physics C number 4, and let's just jump right into it. Unit 8, right? Okay, a loop of mass m and having a total resistance capital R falls vertically through a uniform magnetic field B as shown. So I'm just going to draw this real quick. There's a magnetic field that's into the page. There's some loop that's falling with some velocity downwards. And we're given the dimensions of this loop to be B and A. And we are also, I'm just going to do this really quick. I'm going to denote this side of the loop where, actually not X, I'm going to use Y. I'm going to use this side of the loop that is exposed to the magnetic field B. I'm going to call that distance, or not distance, that length Y. So that length that is exposed to the magnetic field currently is Y. Okay, you're going to see how that will be played. You'll see how that's going to play a role later on. Let's do part A. So part A is, what is the direction of the induced current in the loop? So again, this is right-hand rule, and I'm just going to do it the way that I do it. You can do it however you like to do it. I just put my arm in the direction of velocity, and then I curl into the, I'm curling into the page, which is like this, curling into the page, and I will, because it's my right hand, my thumb will point this way, and that represents the force on the positive charges in the wire, which is going to be the direction of the current. So if we just do that, because I'm taking this right hand rule from the top segment, this segment right here. If we do this right hand rule, we get the current to be going in a clockwise fashion. It's going to look like this. So that is clockwise, therefore A is clockwise. Okay, let's do part B. All right, let me put some more space for part B, because this is a big one. All right, part B. As it emerges from the B field, the loop reaches a constant terminal velocity. Show that the magnitude of this terminal velocity is given by V equals mgr over B squared A squared. All right, I'm not gonna lie to you, this is really bad. So let's do this then. I'm going to start with this equation, which I don't remember what the law is called, but it's just the integral of B dot dA. So this is the magnetic flux. What we're going to need is the EMF, which we learned it to be negative d phi dt, and that negative comes from something called Lenz's law, which states that the magnetic field created by the change in magnetic flux of this, in other words, the induced magnetic field, will oppose the external magnetic field's direction. So that's all it's saying. So this negative, which this is for the induced EMF, this negative represents that kind of like opposing feeling that we're getting from this change in magnetic flux. That's all that negative represents. But just to make the math like a little easier and just to make my head hurt a little less, I'm going to just put absolute value bars. So it's going to be just like this. And we're going to just use the magnitude of the EMF just for this. And it's still mathematically correct, you'll see. But I'm just going to put absolute value bars around it. Anyways, what are we doing? We're taking the derivative of this equation. And what that derivative looks like is ddt of the integral of B dot dA. Now, this is going to confuse some people because the answer that we're getting is B times dA dt. All right, first let me explain how the dot product goes away. The dot product, we just say it's B times dA times cosine theta, and theta represents the angle between B and the vector B and dA. And in this case, that's 0. We can just say that to be 0 degrees. And that will be positive, give us a number of positive 1. So we're just multiplying it by positive 1. So it's just B times dA times positive 1. And now the second part that confuses people is, or which I'm assuming will confuse people, is this ddt. So do you remember the fundamental theorem of calculus? Yes, hopefully you do. Whoops. And what I remember, if you remember, the way it worked was that there was like some 0 to t, it was like this, but these variables differed and they changed with the application of the fundamental theorem of calculus. So in this case, this would be sine x. That would be the answer because it changed. Okay, so I'm going to get rid of that. Okay, so the answer that we get is b times dA dt using the fundamental theorem of calculus. So what do we do with this thing? And remember, I'm using a, what is it? Under normal circumstances, this would have a negative, but I'm just not going to do that. I'm putting absolute value bars. This is the EMF that we just calculated because that is the derivative of d phi dt. It's the derivative of phi sub b. So that's what we just calculated right there, and now we're going to apply it. So dA dt is the big elephant in the room here, and remember how I said I'm going to use y? Well, here's how I'm going to use y. dA dt represents the change in area over the change in time. So if we're going to denote that here, wouldn't you say the area is A times Y? That's the area that's being exposed to the external magnetic field. The only difference now is we want dA dt, which is that derivative. Well, if we want that, all that's going to change is we're going to apply ddt to A times Y, and that is going to be, since A is unchanging, it's constant while this loop falls vertically, Y is changing, and so this ddt will, in a very similar way that the derivative operator applies to momentum, and we get like m change in v, something like that. In that similar fashion, because the mass is not changing for the most usually for momentum, this is going to be A times dy dt. Okay, so now that we have that, we can substitute this into the EMF, and we're going to get the EMF, the absolute value of which will be B times A times dy dt. And dy dt, if some of you probably noticed, since y is just essentially some displacements, we can just denote this as the velocity. So even more astounding is that the EMF is B times A. A is not acceleration. I just want to make sure you guys know that. It's a length, and V being the velocity. So now we can just find what the current is, because eventually we're going to want to use this formula, I, L cross B. I'll explain that in a second. So right now, though, we want to just use Ohm's law, which is this voltage equals I, not IV, sorry, IR. And we want to isolate I because we want to substitute that here, right? So, oops, okay. So I is equal to EMF over R, which is BAV over R. So again, I used an absolute value for the EMF. Let's not forget that. I'm just going to be consistent there. Okay, so that's I. And now we can substitute that into the force. So I is BAV over R. That is our first quantity. L. L is an unchanging quantity here. L represents, you guessed it, it represents A, because that's the length that is not changing in this situation. So L will be A, and B will be B. And this is, since this is happening, the force is going to be perpendicular to this, it'll be sine 90 degrees. So we get an answer of B squared A squared V, V over R to be our force. And this force that's being denoted is our magnetic force. All right, let's explain why we need to use this force. I'm going to draw another diagram here of the loop. Just imagine that there's some part of it that's covered by the magnetic field. So from that magnetic field, there is a magnetic force that is going in the opposite direction of motion, which in this case, from the center of mass, the force of gravity is pushing this rectangular loop down, and this magnetic force is being pushed up. And this will be coming from, this magnetic force will be coming from that change in magnetic flux. With that in mind, we can now solve an interesting equation, which is the net force. I'm sorry, this should extend to the center of mass. And what we get is this net force is equal to the force of gravity, because this rectangular loop still is moving in the net direction is downward. We will get the force of gravity minus the force of the magnetic force. And I'm just going to say force net is ma, and the force of gravity is my battery's running low, is mg minus this equation b squared a squared v over r. And a is equal to dv dt. And yes, many of you are seeing it. We can plug that in here. Many of you are seeing this is becoming a differential equation. So I'm going to divide by m, and we will get g minus b squared a squared v over mr. This is becoming nasty. So I'm going to go to this side where there's a little more space, and I'm going to continue this. So I'm going to multiply this dt. I'm skipping this step. I'm just telling you I'm multiplying this dt to this quantity, and I'm going to integrate. So I'm going to integrate dv, and this quantity g minus b squared a squared v over mr times dt. Oh shoot, whoops. Oh, actually, you know what? Whoops, I made a mistake. I'm going to divide this entire thing. I am sorry, it's been a while since I've done this. I'm going to divide this entire thing, this entire quantity by itself, so we get 1 on that side. It'll just be dt. So basically, I'm also moving this quantity under dv. I'm dividing that. And in Calc BC, you guys are probably very familiar with that. It's been a while since I've done it again, so I'd forgotten. Okay, so this is what we have here. And now we will have just dt, which is being integrated. Now we need to figure out the limits of integration here. And for dt, it's not too bad. We don't really know the time, so I'm just going to do it from 0 to t. But for v, it's a little more complicated. Or actually, no, it's actually not that complicated, because it's a terminal velocity. So we're just going to be integrating from 0 to that terminal velocity. Yeah, actually, yeah, that's it. Both are pretty straightforward for the limits of integration. Never mind. So we're going to integrate, and this is going to become, oh my gosh, sorry. This is going to become very, very nasty. And we're going to get a natural log of g minus b squared a squared v over m r. And of course, chain rule, right? Sorry. We can't forget chain rule. Let me just finish that. There's t here, and this is, we still have not done from vt, so from 0 to vt. There's chain rule here, which means we have to take care of this negative r over b squared a squared v. So that's the chain rule being applied. And then once we integrate this side, yeah, I think that works. So then once we integrate this side, I believe that all we have to do, I'm just going to take this constant and move it over to the other side. It's going to be t times b squared times a squared times v over mr is a negative. And I'll just put an e here because we're going to take, it's just the inverse operation for natural log. This is going to be g minus b squared a squared vt over mr divided by g once again. That's after you integrate. And I really just cannot show the steps right now. It's disgusting. Okay. And now we will just divide and isolate vt. So this will become, apologies, my battery died, so that was weird. Anyways, let's continue this lovely problem. I don't know why I chose this problem. So we have 1 minus b squared a squared vt over mgr, excuse me, which is equal to this e to the negative t b squared a squared v over mr. And I just realized I made a mistake. Okay. Okay. I'm really sorry, but basically this should not be here. V is a variable, not a constant, so that should not be outside of the equation. I was wondering about that just now. So there's no V here. I apologize for any confusion. But yeah, so that's, yeah. Okay. Now we can isolate Vt, which is going to be Vt is equal to, let's try to see if I can do this. 1 minus e to the negative tb squared a squared over mr times mgr over b squared a squared. Yeah, oh my gosh. That was bad. Okay. Now, you may be wondering, what was the point of this hellish display of calculus? Let me show you. Let me show you how powerful calculus is. We are looking for this terminal velocity. And if we remember, all we have to do is plug in at this point what will make this what will make this work. And as you can see, the terminal point is determined when this entire thing becomes sorry about that. As you can see, because as t approaches infinity, we're just going to do a limit. Imagine there's a limit as t approaches infinity here. As t approaches infinity, this term goes to 0. It's just 1. And our terminal velocity is mgr over b squared a squared. And that is right. Oh man, I feel so amazing right now. Okay. Woo! That was really long. And I probably did it way unnecessarily long. But man, does that feel good. Okay. Let's do this last thing. So I ran upstairs to get a charger. Oh, okay. Alright guys, we're going to do the final part, which is part C.
Show that while the loop is traveling at terminal velocity, the rate at which heat is being dissipated in the loop is P equals mg over BA squared R, whatever. The heavy lifting has been done. So all we need to know, oh my gosh, I don't want to update my recovery media. I don't even know what the recovery media is. Okay, so all we have to do here, we've done all the heavy lifting, is P equals I squared R. That's it. And we have I. We have defined, oh man, this looks disgusting. We have defined I, and I is here, BAV over R. So let's plug that in. BAV over R squared times R. And that is going to give us B squared A squared V squared over R squared times R. Now, that is maybe very fine and dandy, but we have yet another substitution to do. Let me just add this VT because we want the terminal velocity to be used here. And yes, we will plug it in once more. We're going to plug and chug again. We're going to plug in VT here, and it's going to be B squared A squared. Oh, mama, here we go. MG R over B squared A squared quantity squared. Whew! Yeah, this is really intense. And then this is all over R. Oh man, this is nasty. Sorry, I forgot this squared here. Whew! Okay. Man, I'm just getting lost in my work here. Divided by R squared times R. And we will see that this cancels, but there's a B squared A squared left. So we get mg squared, m squared G squared, R squared over B squared A squared R squared times R. And these R's cancel out. And yeah, you do get the answer. M squared G squared. Sorry about my very messy work. M squared G squared over B squared A squared times R, or in other words, mg over BA squared times R. That should be power G over BA squared R. All right, that should be power. That should be. Let me look at the answer. Yes. All right, guys. This was painful. This homework is really bad. You should probably get a start on it. Like, yeah, it's a good idea. All right. We'll meet out. Yep. Bye.